Okay, now that we have seen how to compute the distributed losses along your pipe and the concentrated ones in a particular position of your system, we are able to define two kinds of problem. The first one is that, for example, we know all the geometrical parameters defining your system, and you want to compute the volumetric discharge that flows inside the pipe, and this kind of problem are called the verification problems. And the other kind of problems is when, for example, you know what is the volumetric discharge flowing inside your system, but you don't know the diameter of your pipe. So this problem is the project problem, because basically you want to dimensionate the diameter of your pipe. Let's suppose, for example, that we want to solve a verification problem. So let's consider this kind of first example. Basically, right here we have that there are two tanks, 1 and 2, and these two tanks are linked by a pipe characterized by a length L, a diameter G of your pipe, a roughness epsilon. Then we also know H1 and H2, so we know the total head in tank number 1, which is respect a reference system Z equal to 0, and we know also the total head in tank number 2. Another thing that we know is the density and the dynamic viscosity of our flow, of our fluid. So the aim in this case is to compute the volumetric discharge flowing in the system. To do this, what one does is to write Bernoulli's theorem extended to real fluid, in this case from tank number 1 to tank number 2. So we start from this tank, our fluid is moving from this point to this one, and we have this final tank. So basically we would apply Bernoulli's theorem from this point to this one. So how to do this? Total head in tank number 1. So this total head H1, in this case, since the fluid inside the tank of course is in quiet, is equal to the position of your free surface of the fluid. So it coincides with the level in tank number 1. And this is our total head in the first tank. Then our fluid is moving inside the pipe, and in this point there are some turbulences. These turbulences are, remember, given by a concentrated losses, which is K times V to the power of 2 over 2G. But in the case of square-edged entrance, K is equal to 0.5, so minus 0.5 V to the power of 2 over 2G. Then we have what? We have the pipe, and along this pipe there are some losses of energy due to the viscosity of your fluid, due to the diameter of your pipe, of the roughness, and so on. And basically we have seen that it is possible to define these distributed losses by J, which is the hydraulic gradient, times L, which is the length of the pipe. So basically right here you have J times L. J, again, if we don't know what kind of flow is occurring inside the pipe, it is possible to assume the generic form for the computation of J, which is given by Darcy-Weisbach. So again, Darcy-Weisbach says that J is equal to friction factor lambda times v to the power of 2 over 2g times the diameter of your pipe. Hence, this term stands for your distributed losses along the length of your pipe. Then finally, your fluid is entering in the final tank, tank number 2. Hence, in this point right here, you have again another concentrated loss, which is given by K times v to the power of 2 over 2g, where K in this case is equal to 1. Then, when I arrive here, I see the final total head, which is the one given by the total head in tank number 2. Again, since the fluid is in quiet, the total head in tank number 2 is coinciding with the free surface of your fluid, so is the level of your fluid. Alright, so if I want to compute the volumetric discharge moving inside your system, I have to remember basically to apply Bernoulli's theorem, as we have seen right now, and the continuity equation, which says that Q is equal to the velocity times the cross-section area, and these terms remain constant. So, from this equation right here, you can take H1 minus H2 and bring 1, 2, 3 on the right side of the equation, and in the end you obtain this formula, which says that the difference of the first and the final heads is equal to the total losses inside your system. Right now, your only unknown parameter is exactly Q, so you can compute Q starting from this equation. So, the problem is that to do this, you should know how much is lambda. And lambda is something that is depending from your kind of flow, because remember that lambda is the friction factor, and if you want to compute lambda, basically you should check or Moody diagram or the Colebrook-White law. So basically, lambda is something that can be depending from Reynolds, if we are in laminar flow, laminar condition, or it can be dependent both from Reynolds and the relative roughness, if we are in the transition regime, or otherwise, if we are in purely turbulent, is only depending on your relative roughness. So basically, when I compute Q in this formula right here, because no one told me what kind of flow is inside this pipe. Well, usually inside a pipe system, usually you have a turbulent flow. So if someone tells you, well, you know, your flow is moving like a turbulent one, you can forget this term and say that J is given by Chassis' law. Remember? Just going back. Chassis' law says that J is equal to v to the power of 2 over C to the power of 2 times R, and this term right here depends only the the roughness of your pipe. But if no one told you the kind of flow that is inside your pipe, well, you have to make some assumption. For example, according to this reminding right here, if we are looking at case 1 or case 2, lambda is a function of Reynolds, and Reynolds is a function of Q, because Reynolds is, go back for a while, is the density times the velocity of your flow times the diameter over mu, but there's the velocity. So if I'm considering the velocity, it means that I'm considering the volumetric discharge, because remember that the average velocity of a flow in case of incompressible fluid describes exactly the volumetric discharge of your flow. So let's go on and come back to our scheme. So basically, if I am in case 1 and case 2, I have to take into account that Reynolds number is something that is depending on Q, so it's something that is unknown. While if I consider the purely turbulent flow, lambda is a function of the relative roughness epsilon over d, and the regime of flow is not known a priori. So usually what one does is to suppose the regime of flow and the resistance law, then one computes lambda, computes Reynolds, computes Q, and then check what does it mean. So let's try to see it with an example. We start to suppose I want to compute this equation right here, and I don't know exactly what kind of lambda I've got, because I don't know exactly what kind of regime I'm facing. So usually what one does is to suppose that inside the pipe there's a turbulent flow, which means that you're considering case 3 or worse, case 2. Basically, I start to compute the first lambda 0, so I suppose, for example, that my flow is moving like a purely turbulent one, so I enter in a diagram, Moody diagram, with a certain value of lambda 0. Remember that to do this, I have to know exactly epsilon over g. So the first attempt will be to take my data, which are this one. I know epsilon, I know g, so I can compute epsilon over g. I enter in Moody diagram looking at this stuff, and I check. For example, right here I have a range of values of Reynolds number for that are true in the turbulent flow. So I try to check with one value what happens. Hence, basically, I compute lambda 0 from Moody diagram, and once I determine lambda 0 of first attempt, I compute Q0 from this stuff, and then one, of course, has not finished his problem, because remember that we don't know anything about our lambda. So once I've got my first attempt of Q0, I compute Reynolds number, because remember again it's rho vu d over mu. Mu I've got it, rho I've got it, vu is q over a, so it's fine, and g is the diameter, so I've got it. Then I compute this value of Reynolds number, so I'm right here. I have Reynolds 1, then I exactly check the first Reynolds 1 with our first attempt. They are really different, so I repeat the procedure. So again, I take this Reynolds 1, I get a Colebrook white in transition zone, so basically this would turn me on something that is moving in this part. Alright, so again, it's a bit long. I compute with Moody diagram or Colebrook white lambda with Reynolds 1, so I'm right here. And then once I have lambda, I compute again Q1, and then Reynolds 2. no, sorry, Q2 and then Reynolds 2 and so on. So basically the procedure is making a first assumption of your Reynolds number, which means basically to say that you're, for example, in turbulent flow. So take your Moody diagram and evaluate, starting from epsilon over d, your friction factor. Friction factor lambda 0, so of first attempt, you compute, you insert this in this equation, you compute Q, so basically you obtain your volumetric discharge, and then recompute Reynolds, check if the value that we have obtained for Reynolds is very different from the previous one. If it's so, then recompute the friction factor, recompute the Q, and then recompute again Reynolds number. Again, they are different, redo everything all again. So basically, in the end, you stop your procedure when the Reynolds number that you obtain and the previous one are not so different, which means that their difference is lower than the tolerance value. Alright, so basically in this second part related to uniform and permanent motion in pressurized pipes, we have seen, just to remind, how to compute the distributed losses, and we compute basically J to evaluate your distributed losses. Remember that J is something depending on the friction factor, and the friction factor is something that is depending from the nature of your flow or the relative roughness, or both, depending on the kind of flow that you're observing, and the kind of flow is given by the Reynolds number. Then remember again that we have seen how to evaluate Moody diagram and what are the critical formulas for water mains. Then we have concentrated our attention on the valuation of the concentrated energy losses, and so basically we observed some kind of concentrated energy losses for sudden enlargement, head loss at the entrance of the pipe and at the exit of the pipe, and when you have a different kind of geometry inside your pipe. Finally, we have seen an example of two tanks linked by a pipe. One thing that we didn't say before, let's check that when you compute Bernoulli equation from tank 1 to tank 2, basically, you are imposing an equation that is described from the red line in this picture. So the red line right here is something that is similar to this equation right here. In fact, you see that you start from H1, then it decreases off the first concentrated losses, then you have a decrease that respect this horizontal line. It's exactly equal to J times L. So basically respect the horizontal line. I don't know if you can see the hand in this video, but my hand, my cursor, try to describe a linear line like this, an horizontal line, sorry. Respect this horizontal line. This red line is lower than a quantity, and this quantity is exactly J times L. Then again you have V to the power of 2 over 2G and H2. So basically this is described by this. And if you decrease this quantity right here of the kinematic height, you obtain exactly the blue line, which is your piezometric head. And finally, we have seen how to evaluate a verification problem in the case when you don't know exactly what kind of flow, what kind of regime is the one that describes your fluid. So basically, if you don't know it, you are in laminar or in transition or in purely turbulent flow.